Hello all. So I'm excited to be at the Open Source Data Summit today. Along with me, I have Balaji, and we are going to talk about scaling and governing Robinhood's data lakehouse. At Robinhood, we use lakehouse for business critical applications along with analytics use case. In this talk, we will describe the evolution of big data ecosystem at Robinhood, not only in terms of the scale of data stored and queries made, but also the use cases that it supports. Moving on to the next slide. So in today's agenda, first we will be talking about the high-level architecture of the data lakehouse. Next, we will be walking you through the scaling aspect of the system along with some challenges faced. Then we will introduce how we apply data governance on top of our data lakehouse. So moving on to the next slide, talking about the first agenda item, which is the data lakehouse. So what is data lakehouse after all? So if you look at it, this is the bird's eye view of how data moves at Robinhood. Some of the sources from which we create the data lake houses are RDBMS, web and mobile events, third-party data or like external data. So for RDBMS, we have several online relational databases that support our trading, brokerage, and other systems like clearing, etc. Then we have web and mobile events. We capture these events in real time for experiments data and other use cases through our mobile and web app. Then we have the third-party data, and there are a bunch of third-party integrations for which you capture the data into our real-time data lake. Our infra systems provide this raw data to our data scientists, data engineers, and other data analysts or other use cases. They in turn then create many other derived data sets which are used for all the data related decisions like analytics, reporting, fraud, risk, etc. Moving on to the next slide. So let's look at the architecture overview over here and how ingestion happens for one of the critical use cases like RDBMS, for an instance. So onto your left, let's say like you have a primary RDS instance to which an upstream application does all the business critical writes. And this can be any typical application with a tier 1 support. Then next, we have a Debezium component capturing each of those write events from the primary RDS instance and then push them to Kafka. Once we have all the messages in Kafka, then we run our Apache Hudi Delta Streamer, which is a Spark application, either in continuous or batch mode, based on the frequency of ingestion. And this has been set differently for each of the DB tables based on the priority. We'll be going a little deeper into this later on. And then finally, we have the Hive component, which updates the Hive metastore with the location of the Hudi table where it has been written. If you observe, there is a second pipeline right below the top one, which says initial bootstrap. This is the process of creating the initial table in the data lakehouse, on top of which we can apply the delta updates that we discussed in the pipeline above. Moving on to the next slide. So now let's look at how do we actually do change data capture with the Debezium component, which we described in the previous slide. So as you know, like Debezium is an open source Kafka Connect service that supports CDC from many relational databases like Postgres, MySQL, MongoDB, etc. Kafka Connect provides the required infrastructure underneath for scalably and reliably streaming data between Kafka and other data systems. Again, let's take Postgres for an example and zoom into it, like how do we do it over there? So as with many other relational databases, Postgres also maintains something called a write-ahead log, a bin log in other DBs, which kind of tracks all the DB events for enhancing transaction performance, crash recovery process, or other use of standby instances to replay the transactions. Debezium actually subscribes to these wall logs and listens to all the events to begin with. And this is the inception of the CDC or a change data capture, which is then pushed onto the Kafka topics. there is another component, if you see, which is called as Avro, which is our serialization library. Um, we can use multiple types of serialization library. The one which we have chosen here is Avro. Uh, this is then also needed for the ingestion downstream to be for deserializing the messages which are put in Kafka. Going back to the right side of the diagram, the topics to which Division publishes are partitioned for scaling based on the frequency of the updates or the nature of the table, and this forms the very basis of our change data capture, since we get each and every transaction performed on each of the tables in a database. Moving on to the next slide. Now let's look at the actual change data capture and how does it get propagated to the data lake. So let's say the real-time events are getting published to Kafka in their respective, for each of the tables in their respective topics, in which we have all the CDC events residing to be replayed and applied to the lakehouse with asset compliance. We run a Hoodie Delta Streamer job to read those messages for each of the Kafka topics and then write it to the Apache Hoodie table in S3 data lake. And this is where also the Avro schema registry is read to deserialize the message and then apply use the Hoodie write API layer to write the transactions. The other block that you see which says Hoodie metadata or timeline is to basically determine things like it is something which is internal to Hoodie, which helps us in doing incremental ingestion, where we track the last offset of the Kafka where we read it from, and then resume it from there to read the messages since then. Moving on to the next slide. So let's talk about the lakehouse aspect of Apache Hoodie. So what is a data lakehouse? If you look at it, a lakehouse combines features of data warehouse and data lake. Some of the requirements are things like a data lakehouse must be able to store very high quality data reliably with ACID transaction support. It has to be highly scalable and allow decoupling of compute and storage unit elasticity to support varying use cases. It should be using open data formats to avoid data lock-in. And that should be supported with the metadata as well. It should also allow direct access to files, especially for machine learning use cases. For example, you should be able to directly query the S3 prefix or folder where the data is being written. For quick and efficient processing, incremental streaming pipelines must be buildable on top of this data lakehouse. And one more thing which comes up to my mind is there are diverse applications for data lakehouse. For example, it stores both raw data replicated from online database and the other sources which we discussed in the previous slides, which are also derived data sets and other third-party data sources. A lakehouse should be optimized for all these requirements. So at Robinhood, we use Apache Hoodie as the lakehouse platform, as we were discussing. We are currently storing the raw data using in the Apache Hoodie format or the Apache Hoodie persistence layer. And we are also migrating all the derived datasets to use the same API. Apache Hoodie provides transactional support to data lake tables. It also supports table level locking and supports multiple processing engines such as Spark, Flink, and it does allow us to decouple storage and compute. And what it means is that we can also run it with Flink and other kind of engines to do the same incremental processing. That's how Apache Hoodie is also a complete platform for building ETL and ingestion pipelines. It has first-class supports for upserts or updates and deletes along with other operations. It provides native support to implement stream processing over batch data. So let's move on to the next slide So to summarize, Apache Hoodie is built using the same principles as RDBMS and has complete lakehouse platform features inbuilt. For Robinhood use cases, we need reliable near real-time ingestion with efficient ETL support, which is provided by Hoodie. So moving on to the next agenda item, which is operating at scale. So let's look at what steps we took to run production ingestion pipelines at scale. So these are a few of the challenges that we have as a team. So we are a lean team managing more than 10,000 data sources, streaming, RDS, CDC data sources, static data sources, and others, which kind of constitute our lakehouse. The CDC pipeline has more moving parts with disparate systems like Kafka, Spark, Flink, etc. These pipelines are also stateful, as we need to track the consumption and bootstrapping state of the pipelines in case of any data issues or SLA misses or any data corruption. The tables differ in criticality, traffic patterns, and other factors. So they need to be treated differently in terms of configuration and how we do ingestion. Of course, we also need to be cognizant of the cost. Cost is like very important to us, and we want to keep a track of it, where Hoodie helps us in providing those metrics and optimizing the right parameters around ingestion. With any service ownership, we require any end-to-end monitoring for alerts and failures. And that's how we make our system self-healing, so that our on-call load and other factors of the system are reasonable. The last point is about data freshness and quality, which we will be digging into. And we can move on to the next slide for that. Yeah. So one more aspect of our scaling is tiering. So as we were discussing, all the use cases are different in their own way. So how do we really cater to it? So for that, we have built something like we distinguish each use case by tiers. So tier 0 is our critical or continuous mode use case, where we have the data landed in data lake within a few minutes. And any other tiers are based on the frequency of ingestion and best effort in some cases. So how do we achieve that? Part of it is actually done via resource isolation. So as we were talking about Debezium, Kafka, and Spark jobs, we have resource isolation set at each level. For Postgres, we have replication slots, multiple replication slots created for each of the use cases with a certain limit again, because they come with a small cost as well. Then we have resource isolation for our Debezium connectors, where we have connectors connected to each of the DB tables, separate connectors connected to the DB tables. And then we also have compute and storage resource isolation by building swim lanes and different clusters to process the data based on the criticality of the pipeline. Lastly, we also have SLA guarantees with freshness. And what we do there is, we can move on to the next slide where we talk about it. So any live data is in data lake is only as good as if we know the freshness of the data, that if the downstream knows the freshness of the data. So that's why tracking freshness of the CDC tables are important. Downstream pipelines can only be started after the CDC tables are known to have fresher data than a cutoff time. But in CDC tables, it's not that straightforward. There are multiple hops, and we need to know the freshness of each of the stages based on like the architecture diagram that we saw before. There's also challenges around things like slow-moving tables, where the change is very infrequent. So we don't have a steady stream of data to reduce freshness. Next slide, please. So the freshness pipeline that we have built here is, again, riding on the same infrastructure that we use for CDC ingestion. Debezium maintains a state of the connectors in a separate keyed Kafka topic. Apache Hoodie does a Delta streamer ingestion in continuous mode from this topic and creates a similar data lake table. Now, at the same time, the actual data pipelines, when they do ingestion, they also log their transaction metadata along with the freshness. Could you click on next? Yeah. From the they also produce the transaction metadata along with the freshness from the Debezium messages which has been processed into a separate Kafka topic. Finally, there is yet another Hoodie data streamer job that reads these stats from both the data sets, joins them, and then gets the freshness information at the table level. We upsert the table freshness information to a different Hive table, which are then queried by downstream for their job to wait on a certain point in the freshness timeline. Moving on to the next slide, this is how our typical freshness metrics look like. So if you see, we have different tiers of freshness. Some of them go for 10 minutes, some of them are under few minutes. And this is how the tiering also works. I would wrap up the conversation around Apache Hoodie and Data Lake over here and pass it on to Balaji for the next part.
Thanks, Pritam. Let's look at how we are architecting our lakehouse for data governance and GDPR compliance. So our main goal for data governance in Robinhood is to make high quality data be discoverable and usable for both existing and new data applications, while also being compliant with different regulations. There are many aspects to data governance. The first, we need an ability to track all the data assets and the lineage flows end to end. Then the data organization and controls of the lakehouse needs to be conducible to both new and evolving regulations. We also need ability to employ effective oversight of data assets so that we can unlock their value and impact. We need support for fine granular access controls and manage data obfuscation and other techniques to handle personal data. Finally, we also need ability to assure data quality and track them through metrics such as data accuracy, completeness, and freshness. So given the high-level objectives, we then came up with what we need in the data lakehouse ecosystem to support effective data governance. The first and foremost thing that for us was to build the right foundations on which we can employ effective data governance. We needed like proper systems and processes to discover data assets, both online and offline, understand the ownership, data, understand the semantics and the lineage across the flow end to end. Next, we also needed guardrails to be implemented at the architecture level so that we can isolate sensitive and non-sensitive personal data, production versus test data sets. That's crucial for data accuracy and other essential handling of these data sets. Also, raw and derived data sets needs to be distinguished so that like we can have proper access controls and boundaries between these. We need ability to support differentiated quality of services for these data sets based on the criticality, like in terms of their business usage. So then we need the lakehouse, just holding like petabytes of data to honor all the GDPR regulations, such as users' rights to deletions. Also, like finally, we need the ability to grant, audit, and revoke accesses to different data sets in our lakehouse, and also keep track of the purpose for which these access requests are being made. So yeah, these are the fundamental system requirements that we came up with, and we will look into the top three of these ones like in more detail in the coming slides. So regarding the foundations, like, so we realized like we needed not only to track the lakehouse data sets, because the lakehouse is basically a downstream to all the online data sources that is being stored in different OLTP databases. So we need a first-class service to keep catalog of all data sets, both online and offline. Online, including like those stored in Postgres, DynamoDB, and streamed via Kafka, as well as online as well as the offline data sets in the lakehouse. So the way we approached is like we employed we built a first-time service, and we employed user tagging-based approach where ownership, sensitivity, and purpose-related meta tagging are tagged by the owners. So for lineage, for the lakehouse data sets, we used Data Hub. We have around 50,000 plus lakehouse data sets, and we captured all the lineage in lakehouse through instrumentation. And we not only capture dependencies between the data sets, but also between data sets to ETL jobs and also to dashboards. And that gave us a good set of discovering the lineage for all the different processing that are happening on the lakehouse. As we rely on user tagging for some of the sensitivity information for the data, we have to manage the tagging quality. So we took an approach where the tagging is done in code, which is co-located with schema files, so that any schema changes, like such as like adding a new table, can be cross-checked with the link checkers using code review tools to ensure that we have proper coverage. In addition, we employ tools like PI scanning for on our lakehouse data sets to catch any tagging inconsistencies of both the lakehouse data sets and their upstream, which are the online data sources. So moving on, so that was the foundation aspect. Then regarding the lakehouse organization itself, as I mentioned, like we need to isolate sensitive data and also on other different dimensions. So we are organizing the way we are doing it is we use the approach of creating zones, which is basically, think of it like a sub area within the lakehouse. And the way we did it is like we have in this case when we ingest the data from online data source, the ingestion service will land to one of the two zones. The one on the left is a non-sensitive raw zone, which has no personal data or personal data stripped or masked. In on the right side, there is this raw zone where data sources which are marked with sensitive data tagging will be landed on those zone, and we track purpose of the usage and everything and ensure that it is correctly used. We have guardrails at the zone level so that we prevent, for example, we prevent a job which has read permission on sensitive zone to get a write permission to non-sensitive zone. This ensures that like at the system level we can ensure there's no PA leakage getting leaked to a different zone area. Just like raw data, we have the derived data also that have two different zones. One is the non-sensitive derived zone and the sensitive derived zone. We have infrastructure managed anonymization jobs that performs masking to anonymize user data to allow landing to non-sensitive derived zones. We will be like in future, like our plan is to also implement sampling and other non-sensitive derived data copying so that they can be used for pre-prod and ad hoc testing. So next we will look at the one of the core requirement for GDPR, which is the GDPR data deletion in the lakehouse. So again, like GDPR regulation requires users' right for the data to be forgotten. And with lakehouse, with petabyte of scale of data, we typically have tons of historical data, including personal data. How do we, which makes deleting specific users' data a needle in a haystack problem. So the approach we took as like three aspects. So first, we masked personally identifiable information for use cases, which needs to honor user deletion request. We keep the mapping between user PI data to mask value protected so that they are in a separate mapping table in a sensitive zone. For other use cases, such as financial reporting, we keep the raw PA data in sensitive zone. With the mask approach, the PA data is isolated to the mask basically is just a non-sensitive raw zone, and only deletion needs to be applied there. So we use the masks themselves are basically generated using specific salt. We will go into in depth in the next slides. So we maintain these specific user salts per user, and we use that for masking. The second aspect is that we employ a masking of the entry layer at the entry layer itself while ingesting the lakehouse. This allows us to platformize the whole masking approach. We can have a coherent anonymization strategy to which can be implemented centrally by the ingestion team, so that like the downstream do not have to reinvent the wheel. This also allows keeping the blast radius of the tables where deletion needs to be applied to be minimal. So finally, we use Apache Hudi for which can perform efficient deletions of these mapping tables without having to rewrite the whole table. Okay, so diving more into the masking requirements. So we need the masking function to support properties such as consistency. For example, for one user, we need a single consistent mask value to be generated every single time for the same PA value. We also need the divergent properties, which means like for two different users, even though they share the same PA value, we want the mask value to be different, so that like deletion can be applied specifically for that to a one particular user without having to affect the other user. So then there'll be cases where deleted users will reappear. We still need to support forgetting old data, so prior to reactivation. So also finally, we need cost efficiency when it comes to mask generation and PA deletion. We need to be as much effective as possible. Okay, so in Robinhood, we have different backend teams, vertical teams. They have their own notion of identities, such as account IDs, user IDs, or any other internal IDs to identify user data. The challenge for us as to, from the lakehouse perspective, is to, as we ingest all these different data into the lakehouse, we need to maintain the properties of consistency and divergence, as I mentioned in the previous slide, with the setup. And yeah, so final slide, like, so just to put everything in perspective of how did we implement these properties. First, we created a first-class service that keeps track of mapping all these different identities and translating them into a unique lakehouse identity. And we assign specific salt for each of these lakehouse identities. So whenever we are ingesting upstream data into the lakehouse, the masking ingestion service retrieves the corresponding salt and creates the mask table, which maps the mask value to real PA value, which is kept in the mask table is kept in the non-sensitive zone, whereas the actual mapping table, which maps the real mask to the real PA, is kept in the sensitive zone. The backend IDs in this process of transformation, like the backend IDs that we get from the upstream, are translated to the lakehouse ID. The user PAI is masked with the retrieved salt, and then the actual mask value is stored in the non-sensitive zone and also in the mapping table with the translation. So finally, when we receive a deletion request, the lakehouse deletion orchestration would basically leverage Apache Hudi to perform deletion operation of specific rows in each of these mapping tables. As PA access are through these mapping tables, we are able to honor the right to be forgotten through this mechanism. And yeah, so finally, so the open source Apache Hudi is the central component here for us that enabled us to operate our lakehouse efficiently and also meeting our SLA and achieve GDPR compliance. And yeah, thank you for this opportunity.